Hi everyone. Today I'd like to talk to you about the kinematic equations in physics. Now, our goal here is to use kinematic equations to solve problems for objects moving in a straight line at a constant acceleration. Now, we'll also talk later on about how we can solve problems for objects that aren't moving in a straight line using these tools. But to begin with, we're just going to talk about motion in one direction. Now, we've played around with graphs and using graphs to solve motion problems, but there are times when that's not always the most effective or efficient way to solve a problem. So today we're going to add these kinematic equations, which are kind of like tools in your toolbox, other ways to solve problems, sometimes more efficiently than the tools you may already know. These tools are going to focus around 5 key variables: v0, the initial velocity of an object; v, its final velocity or current velocity; delta x, its displacement, or if it's a vertical motion problem, that could be delta y; a, the acceleration of the object; and finally t, the elapsed time. The kinematic equations themselves, there are 3 of them. The first says that the final velocity is equal to the initial velocity plus acceleration times time. The second says that the displacement is equal to the initial velocity times time plus 1/2 times the acceleration times the square of the time elapsed. And finally, the final velocity squared is equal to the square of the initial velocity plus 2 times your acceleration times your displacement. Now, to utilize these equations, we're going to go through a very specific set of problem-solving steps. And solving these types of motion problems is actually very straightforward if you follow this procedure. The key to solving these efficiently is taking the time to set them up properly. If you go through this too quickly, it's very easy to make a mistake. But once you have the setup down, then the problem solving itself, the algebra, gets really, really easy. So our first step is always going to be labeling our analysis for a horizontal or vertical motion problem. If it's horizontal, we're going to call that the x direction. If it's vertical, we'll call that the y direction. And we only ever look at a table of information for either horizontal or vertical at any given time. We don't intermix those. Later on, when we talk about projectile motion, objects that go in both the x and y, we'll still have separate tables, one for horizontal and one for vertical motion. Next, we need to choose a direction to be positive. And the easiest way to do this is if you pick the direction of an object's initial motion and call that positive, it's consistent. You really can pick any direction you want, but if you're consistent, you'll always be doing it the same way, less chance for error. Next, we'll create a motion analysis table where we write our v0, v, delta x, a, and t, and fill in the information we know, our givens. Finally, when we know any 3 items in this table, we can always solve for the other 2. Let's see how this works in practice. Our first sample problem has a race car starting from rest, and it accelerates uniformly at a rate of 4.9 meters per second squared. What's the car's speed after it has traveled 200 meters? Well, of course, this is a horizontal motion problem, and we'll call to the right the positive direction, say that it's moving that direction. So our first step then is going to be to fill in our tables. We'll start off with v0, v, delta x, a, and t. Now v0, if it starts from rest, must be 0. It accelerates at 4.9 meters per second squared, that's a. And we want to know its speed after it has traveled 200 meters. There's our delta x, our displacement. We're looking for its speed, that's v, and we don't know t. Now, of those 3 equations, we need to choose one that has as many of those as possible in there. And right away, an equation that pops to mind is going to be v squared equals v0 squared plus 2a delta x. Now that we have our formula down, we'll solve for the variable we want, get that by itself, v, and that's already on the side by itself, so we're good there. We'll substitute in with units. V squared equals v0 squared, that's 0 squared, plus 2 times a, 4.9 meters per second squared, times our displacement, 200 meters. Or, little calculator work, v squared equals 1960 meters squared per second squared. But I don't want v squared, I want v. So I'll take the square root of both sides and find that v equals plus or minus 44.3 meters per second. And common sense tells us that if we're calling the direction to the right positive, that we must want the positive root. Put a box around our answer, and we're all set. Problem 1 down. These also work for vertical motion problems. An astronaut standing on a platform on the moon drops a hammer. If the hammer falls 6 meters in 2.7 seconds, find its acceleration. This is a vertical problem, and the initial motion of the hammer is going to be down, so we'll call down positive before we make our table. V, V naught, delta y, a, and t. If you drop something, its initial velocity must be 0, so we'll fill in v naught as 0. It falls 6 meters vertically, delta y must be 6 meters, in 2.7 seconds. Time elapsed 2.7 seconds. We're trying to find acceleration, and we don't know its final velocity. That's all right. We'll pick an equation that has as many of the things we do know as possible. And the one that comes to mind is delta y equals v naught t plus 1/2 at squared. And what's really nice about this problem is if we look, v naught is 0, so 0 times anything is 0. This simplifies to be delta y equals just 1/2 at squared. Solve for a first. A equals 2 delta y over t squared. Substitute in with units, 2 times 6 meters over 2.7 seconds squared. Handy dandy calculator tells me that this should come out to be right about 1.6 meters per second squared. Problem number 2 down. That easy. The hard work is really all in the setup. Let's look at one more where I throw a little bit of a monkey wrench in there just to see how you handle it. Another car problem. This time the car is traveling on a straight road at 15 meters per second. It accelerates to a speed of 21 meters per second over 12 seconds. Find the distance traveled. Well, we've got a horizontal motion problem again. We'll call to the right positive. And as we make our table, v naught, v, delta x, a, t. v naught now, our initial velocity is 15 meters per second. Our final velocity is 21 meters per second. And it takes it 12 seconds to do that. We know 3 things, so we know we're able to solve the problem. We're asked to find distance traveled. And it doesn't tell us anything about acceleration. Now, when I go to my kinematic equations to choose one that has v naught, v, delta x, and t in it, I don't have one of those equations. However, what I can do is I can solve for a first and then solve for delta x. So if I solve for the acceleration first, I could use v equals v naught plus at, rearrange this to solve for a equals v minus v naught over t, substitute in with units, 21 meters per second minus 15 meters per second, all over 12 seconds. 6 over 12, a equals 0.5 meters per second squared. A is no longer unknown, it's 0.5 meters per second squared. Now, to find delta x, I can choose any equation I want that has delta x in it because I know the other 4 items in the table. Let's choose delta x equals v naught t plus 1/2 at squared. Delta x then, I substitute in with units, equals v naught, 15 meters per second, times t, 12 seconds, plus 1/2 times a, 0.5 meters per second squared, times t squared, 12 seconds squared. plug all that into my calculator, and I find delta x equals 216 meters. All right. What I'd like you to try and do is create your own horizontal motion kinematics problem. Of those 5 different variables, give the solver 3 of them. Try and make a creative problem, make a story, and see if the solver can solve for the other 2. And then you solve your own problem on the back of the sheet. Decorate it if you want, make it as interesting as you can, make it funny, doesn't matter. Just get some practice doing that for a horizontal problem. And then why don't you try one where you're making your own kinematics problem for something that's moving vertically, up and down. See if you can solve that one too. And if you need more help, of course, you can go check aplusphysics.com. Thanks. Have a great day.